Okay, all right. So, well, welcome everybody for our for the new edition of our webinar series that are combinedly put together by the Missouri Center for Transportation Innovation and the Center for Healthy and Durable Transportation. We have given a short break over the summer, and now we're starting with today's webinar again. We have three very good presenters today, and before I introduce our presenters and they start with their presentations, I want to say again, the Q&A box is open to everybody. So during the presentations, please use the Q&A box to put in your questions. And at the end of their presentations, we'll have 5 to 10 minutes for Q&A sessions, and we'll try to get to everybody's questions in that box. And that's it. So our first presenters are from University of Louisville, Kentucky. Dr. Sun is a professor and chair of the Civil and Environmental Engineering Department at the University of Louisville. She received her PhD in civil engineering from Northwestern University, and her expertise lies in concrete early age properties and testing, concrete durability, and application of waste materials in concrete. She has published over 130 technical papers in journals and proceedings, and she's a member of ASCE, ASWE, and ACI. And together with her, we have also Dr. Moorthi, who's a postdoctoral researcher in the Civil and Environmental Engineering Department, again, at the University of Louisville. And he completed his PhD in Construction Technology and Management from IIT Bombay, India. And his research area of exposure includes valorization of waste materials for construction, rheology of colloidal suspensions, and target-based synthesize and testing of chemical admixtures. He has also published several research articles in reputed journals and conferences, and also co-authored 2 books on basic testing and advanced characterization of construction materials. All right, so with that introduction, they're the first presentation. So maybe Dr. Sun, you can start sharing your screen.
Thank you, Dr. Harmon. Good afternoon, everyone. Thank you for this opportunity to let us talk about research that we've done in our group. So we are trying to convert agricultural waste to cementitious materials. So in today's presentation, we will talk about why we want to do this research and how we did this research and what are the significant outcomes of this work. But first of all, let's start with cement. And we all know that cement is the mostly used man-made materials in the world. And however, producing cement will produce large amount of CO2. So typically, when you produce 1 ton of cement, you release 1 ton of CO2 to the air. So there are a lot of researchers and also ongoing researches to find out how to minimize the CO2 release from the cement industry. So one option can be we're trying to reformulate the clinker phases that we use to produce cement. Or we can also use a different type of binder, such as LC3, that has been quite a hot topic recently. But typically, what we do in cement industry is to partially replace cement with so-called SCM, supplementary cementitious materials. So there are several SCMs that are typically used on the job site. Fly ash, for example, and slag, those 2 are the most commonly used. However, fly ash is a byproduct of coal combustion power plant. And due to the closing of these plants and the fly ash, the supplies now goes down dramatically. And slag, on the other side, is a byproduct of the iron industry. And since we are switching from the for the furnace to the electric furnace, so the supply for slag also drops. However, the demand for both materials, they both go up due to the sustainability issue. So therefore, a lot of people are doing research to seek the other options that can be used as the SCM. And in recent years, there are a lot of ongoing researches to see how to use agricultural waste as supplementary cementitious materials. And maybe you have been heard of research on rice husk ash quite a bit. Rice husk, for example, this type of plants, they belong to the so-called Poaceae family or plantain kingdom. And this type of crops, they have a high amorphous silica content in it, which makes it a good candidate to be used as SCM. Typical plants or crops under this family are corns, rice, wheat, bamboo, and sugarcane. So if we take a look at the distribution or production of these crops all over the world, and we can find that like in India and China, and also European and some other Asian countries, they have rice husk a lot. They produce rice a lot. That's why rice husk is more available there. However, in US, what we produce are corns and wheat and soybeans. So those are the top three agricultural crops that produced in US. And here, corns and wheat, they belongs to the family that we mentioned, which has a high content of silica in it. Now in US, if we take a look at how much corn stover that we produce each year, it's over 200 million tons. And for wheat, it's about 45 million tons each year. If we just think about these two products and to combust these two products to make them so that called ash that can be used in cement, even though that will also cost some energy. However, the temperature that you use to combust those corn stover ash and wheat straw ash are way lower than the temperature that you use to make cement. That makes a low environmental footprint for CO2 that released to the air. If you think about if we just consume like 50% of the corn stover ash and or the wheat straw that we produce in US each year, and that can help to cut off 9.5% of cement production, which means the less CO2, 7 million metric tons of CO2 will be released or will be reduced compared to the traditional cement manufacturing. However, these agricultural ashes cannot be directly used in cement. This is due to the impurities that you have in these materials. And they typically have very high alkali and contents and earth metals that they will inhibit hydration of cement. And also there might be a lot of unburned carbon in it to increase the log of ignition in cement. Therefore, if you want to use these ash as a cementitious materials, and then most of the time you will need to do so-called pre-treatment for these ashes. And there are three typical ways that you can pre-treat your material. You can do it chemically. That means we can use acid or basic solutions to remove the impurities. Or you can use thermal treatment. That means you heat your sample to a high temperature so that the impurities will be gotten rid of. And you can also grind your samples. And this is called the mechanochemical reactions. While you're grinding, and you generate heat, which will also help to remove the impurities in your material. So for those ash treatment, the chemical treatment will be the most feasible way because the acid treatment can help to, researchers found that acid treatment can help to remove the impurities quite efficiently, and also it helps to increase the amorphous silica content in your material. However, there are a lot of uncertainties in the acid treatment. So it's currently in US, there's no standard procedures that we can follow to treat our agricultural waste by using different types of acid. And so there's nothing say that we need to use a certain concentration, so we need to figure it out. And also the treatment duration is another question that we may have in our mind, and the temperature, and also the concentration of the acid and the ash to acid ratio. These are all undetermined. Therefore, to uncipher this black box of the acid treatment, we need to conduct some systematic research. So in our group, we kind of nailed down our methodologies. Like once we have the corn stover, so we will initially burn it at a low temperature to make ash from it. And once we have the ash, then we will grind the ash into the powders, and we let all of the powders go through number 200 sieves so that they have comparable size to cement. And then we will use water wash or acid wash for the material. For the water wash, and we use it as a reference. And so you study the impurities in the leaches that you get. But for the acid wash, we decide to use 3 different types of acid. We use HCl, the hydrochloric acid, nitric acid, and sulfuric acid. And for each acid, we will have 3 concentrations. We'll have 0.1, 0.5, and 1 mole per liter. And then we also have 3 acid to ash ratios, which are 2.5, 5, and 10. Then after that, we will wash the ash, and then we will filter it, the ash, the residual, which on the solid, we will use the water to wash it again to get rid of the acid residual, and then we will dry it, then we will calcine the solid. And for the liquid that we get, we will analyze the composition of the liquid to see whether the impurities, the efficiency of the removal for the impurities. After we have the calcined ash, and then we will mix it in together with cement to look at the hydration. So here are the materials that we used in our research. We have type 1L cement. We have fly ash as another reference to compare with the corn stover ash that we developed. And every time when we replace the cement with ash, we always use 20%, which is consistent with the current practice of KYTC. And then we used 0.5 for water to binder ratio for all of the paste that we did, and 2 different calcination temperatures. For the material characterizations, we used XRF, and we also test log-on ignition. And we used the ICP-MS method to look at the leachate, and then we will show the results. And we also use the TGA method to look at the composition in the paste so that we can calculate the CH amount, and then we can use that as an indication of the secondary hydration or pozzolanic reaction in paste. And then we also use the calorimetric method to measure the hydration of the paste directly. So here are some pictures that we took in the process of the experiments. And these are the raw corn stover that we obtained from Idaho National Lab. And then after that, we burn it at low temperature, and you will see those blackish color ash. And then we grind them and we filter, we sieve them. So they all pass through 200, number 200 sieves. And those are the fine powders. They're actually clumped together. And then we did acid treatment. And after acid treatment, we wash it, and then we dry it, then we calcine it. And this is the final product that you see. So for all of our powders, we also did SCM image analysis. So you see a typical picture for type 1L cement, and then that's the fly ash we use. And then on your right, this is a picture of the corn stover ash, which was calcined at 500 degrees. And we also did the XRF analysis to look at the oxides in the material. And you can see that for the calcined ash, both 500 and 650 degrees, and we actually have a quite high amount of silica in it compared to fly ash, and the silica content can be higher even. And the alumina content is lower than what's in fly ash, but it's comparable to the type 1L cement. We also going to pay attention to the alkalis in the corn stover ash that we obtained. So if the potassium content, they are way higher than the type 1L cement and fly ash, and so does the chlorides. So those things may hinder the hydration of cement, and so we will try to remove them through the acid treatment. So what you see here are just from the water wash. So if we take a look at the ash calcine at 500 degrees from just water wash, and we can see that you can still see the fiber structures of your material. And then if we enlarge, for this picture on your right, you actually see a lot of deposits on the surface of your material. So if we enlarge into that area and also do the EDS, and we found that lots of these deposits, they're actually silica. So which gave us a important message is these materials actually has a great potential to be used as a SCM if they're treated properly. So from there, we thought after water wash and calcine, we already see silica in it. And so our next goal is to remove the impurities through acid treatment. So as I mentioned, we have 3 different types of acid. We have 3 different concentrations, and we have 3 different acid to ash ratios. But we want to keep the consistency in all of the procedures that we use for all different types of acid and all these variables. So first thing we need to decide is how long we got to wash these ashes so that the impurities can be removed effectively. So we did an initial study. We used the HCl as the acid and low concentration there. And we washed our ash for 2 hours, 4 hours, and 6 hours. And after that, we analyzed the composition in the leachate by using this ICP method. So ICP is it's inductively coupled plasma. It's a method that helps you to identify and also quantify the elements in the sample. How it did it is by converting the samples into ions. And then Then these ions can be separated by mass to charge ratios using a mass spectrometer. So once you analyze the liquid, and you will see the concentration of all these sodiums, potassium, calciums, and magnesium. So what we see is only if there's potassium, there might be a little bit difference, but pretty minor. All others, 2 hours, 4 hours, or 6 hours, there's almost not much difference. So due to the length of each experiment and total amount of the experiments that we got to conduct, so we decide to wash the ashes for 4 hours for all of the experiments. And then starting from now, and then we will use 3 different type of acid, and then 3 concentrations, and then 3 acid to ash ratios. And Moorthi can take over from here.
So thank you very much for the comprehensive introduction and the background. So after deciding the washing time, what we had with acid washing as 4 hours, then we started to use different types of acids to understand how well the alkali metals and heavy metals can be removed. So in the next slide, we'll see the effect of concentration, how the concentration affects the removal of different ions in the system. So we could understand from here that when we used hydrochloric acid as a acid to pre-wash the material, and when we analyze the leachate, increase in the concentration of the system, it actually increasing the concentration of the hydrochloric acid, it enhanced the amount of impurities which is released from the system. And also, if we see in terms of like heavy metal release such as aluminum and iron, it becomes very selective because for a lower concentration of 0.1 normality, the amount of heavy metal which is released over here is like very minimum. However, when we increase the concentration to 0.5 normality, there is a significant release of aluminum, iron, and manganese from the constover ash what we have. Next, coming to the effect of different types of acid what we have. Here we can see for all the constover ashes what we had, we washed the acid constover ash with hydrochloric acid, sulfuric acid, and nitric acid at 1 normality at similar acid to acid ratio. So here we can understand that acid becomes very selective in removing particular impurity from the system. For example, in this particular figure, we could see treatment with nitric acid enhances the potassium release in a lot better way and calcium release in a lot better way. And when it goes to heavy metals, and also we can see here that when we use 1 normality nitric acid, we had a higher enhanced release of aluminum from the system and compared to hydrochloric acid and sulfuric acid. So based on this, we use the treated material, calcined this material and substituted with cement and try to understand how the different treatments affects the reactivity and the hydration. So in the next slide, I will be speaking about the effect of replacement of this treated material on the hydration. So for hydration method, we use isothermal calorimetry to measure the heat release from the system. So this particular experiment was conducted for 7 days at a constant temperature of 23 degrees centigrade. And to understand the reactivity, we used thermogravimetric analysis, and this samples the cement and the 20% replaced constover ash samples were cast and kept for 28 days, and the following method was used to understand the presence of CH in the system, calcium hydroxide in the system. So initially coming to the hydration studies, in this slide, we will see how the effect of calcination affects the heat release from the cement. So this particular slide, we can understand that with respect to OPC, when we replace cement with 20% of fly ash, obviously fly ash, the reactivity is a bit slower, and it also dilutes the system, which leads to a reduction in the heat flow. And when we replace cement with constover ash, which is calcined at 500 degrees centigrade, we could see that the presence of impurity is not released, not taken out completely, which leads to higher dormant period when compared to the fly ash, and also a reduction in the heat flow, which we can observe here. But however, when we replace the cement with the constover ash, which is calcined at 650 degrees centigrade without any kind of pre-treatment, we could see there is a very huge increase in the heat flow, which shows that the reactivity is boosting high, and also it becomes dormant period which gets reduced. Coming to the next, this could be because of two reasons. One is the constover ash, which is calcined at 500 degrees centigrade, had a higher amount of unburned carbon in the system, which is almost 5.4%. And in case of when we calcine it to 650 degrees centigrade, the unburned carbon reduced to 1.8%, which correspondingly increases the reactive silica and the alumina in the system. In the next slide, we'll see how the different types of acid which affects the heat, the hydration reaction in the system. So when we used the constover ash, which is treated with hydrochloric acid of 1 normality, we could see that the heat release gets enhanced, and also the dormant period is like almost similar to what we see for the original cement. And similarly, when we use nitric acid and sulfuric acid, the pattern is almost similar to the OPC. However, when we see for the ash which is treated with sulfuric acid, we could see very clearly that the sulfate depletion peak of the system shifts to the right mode side. So if this happens, we should be careful about using sulfuric acid as a pre-treatment method, because the ethicate formation, the sulfate depletion peak shift to the higher value, which means that the ethicate which is forming in the system is forming a delayed period, which might lead to soundness related issues. So that may cause problem when during a hardened property and durability related properties in the future course of time. And when it comes to like using the calcined ashes at 650 degrees centigrade, we could see that the pattern is almost similar when we are using the treatment with different kind of acids like hydrochloric acid, sulfuric acid, and nitric acid. Then we went on to understand the reactivity of these different systems. So for that, we used the thermogrametric analysis as mentioned earlier. So in this method, we try to quantify the amount of calcium hydroxide in the system. So the calcium hydroxide is something which is formed during the primary reaction between the cement and water, which leads to formation of the primary binding product called calcium silicate hydrate and the calcium hydroxide. So when we start substituting the cement with supplementary cementitious material like fly ash or the treated ashes what we have, based on the amount of silica in the system that can react with this calcium hydroxide formed and turn it to secondary CSH. So measuring the amount of CH in the system can be indirectly used to know what is the reactivity or the amount of CH balance in the system, which actually tells about the reactivity of the system. So lower the calcium hydroxide in the system, which means the reactivity of the system is really higher. So from this particular graph, we can see that the material when we replace, which is treated with hydrochloric acid at 0.1 normality and calcined at 500 degrees centigrade, we could see that the amount of CH present in the system is like pretty lower, which shows the reactivity of this particular system is really good. However, when we increase the concentration of hydrochloric acid treatment to 0.1 to 0.5 and to 1, we could see there is a significant increase in the CH in the system, which means that even though if we are using an acid with higher normality, it removes a higher amount of impurities from the system, which doesn't suggest that the reactivity will be in a proportionate way. So we should be very cautious about using a specific acid to understand how the impurities are getting removed and how it is affecting the reactivity. Similar to this, we use ashes which is calcined at 650 degrees centigrade. We could see there is a difference in the way in which the system is getting reactive and like how well the CH in the system is like consumed in the system. So other than this, we actually extracted the purest form of silica from the agro residue. For that, like the pre-treatment method what we showed earlier, we used like the treatment what we showed earlier, like I'm showing it again. So constover, we burnt it under 250 degrees centigrade. And the ash what we obtained, we ground it and passed through number 200C. Then we used 0.1 normality hydrochloric acid, which gave the best reactivity in terms of like CH consumption. And after washing it, the residue what we obtained, we water washed and dried it and calcined at 650 degrees centigrade. And then this material, what we prepared from the hydrochloric acid treatment, we used the sol gel method to separate out the purest silica from the system. And we used two different types of process parameter to optimize it. One is we varied the CSA to sodium hydroxide volume from 60 ml to 150 ml. And then the normality of the sodium hydroxide also varied from 3 normality to 5 normality to identify which could be the optimum value to synthesize this amorphous silica from the system. So this figure which shows the gelation process and the silica which is obtained from that after filtering and drying and grinding. So coming to the silica extraction process, the results of that, we could see very clearly that in order to know whether the silica what we extracted is comparable to the commercial silica what we have. So in this particular figure, we could see FTR image where like the silica in the system, which is having a bond between like silica and oxygen, we could clearly see it between the range of 2250 to 2500. And the depth of the SiO-Si asymmetric stretching, which actually enhances between this 1000 to 1250. And also we could see that the intensity is getting increased when we are increasing the normality of system more and more. And to confirm whether we do have any kind of impurities in the system other than the silica, we did an XRD analysis. So initially when we used the silica as such, which is synthesized from 5 normality without any kind of water washing after the synthesis, we could see that there are a lot of deposits of sodium chloride in the system. So in order to remove the sodium chloride, we actually washed again with water for 2 to 3 times to know to get rid of this NaCl, and then we could get the amorphous silica from the system, which is comparable to the commercial silica what we had. And then some physical properties also we tried to understand. In this case, the two properties what we understood is like the specific surface area of the material by BET method, where the commercial silica had a very high BET surface area of 341.94 meters square per gram. However, when we increase the normality of the synthesized silica what we have, the sodium hydroxide normality, we could see that the surface area starts decreasing. This is mainly because the pore volume in the system starts decreasing when we increase the normality of the sodium hydroxide, which leads to reduction in the surface area of the system. So the significant findings what we had from the study are based on the acid washing what we did, we determined the 4 hours as the optimum level of acid washing what we give in order to leach out most of the impurities from the system. And specifically, when we increase the acid concentration more, the alkali in the system and the heavy metal release from the system increases. But however, for a heavy metal release, the concentration becomes more selective. We need to increase the concentration at least to 0.5 normality for any kind of acid what we are using in order to leach out the heavy metals. And when it comes to the type of acid, nitric acid is the one which has the most effective way in releasing, leaching out the impurities, especially the potassium, calcium, and aluminum. And coming to the hydration reactivity studies, we could understand that calcination, obviously, it improves the reactivity by reducing the loss on emission of the system and increasing the amorphous silica and alumina in the system. And when it comes to that like specific type of acid treatment, if we are going to pre-treat the ash with sulfuric acid, we need to be very conscious because treatment of sulfuric acid leads to a higher amount of sulfate in the constover ash what we have. That might result in decomposition of ethicate in a later stage, which we can observe from the hydration peaks what we have. This might lead to some kind of hardened related property problems in the later stages. And when it comes to TGA reactivity results, we could clearly see that if we have a very acid which has like a very good higher, which has a good efficiency in removing the impurities from the system, which doesn't mean that has the highest reactivity. So to understand this in a more better way, we are doing furthermore material property related material characterization related researchers to understand how this affects the reactivity. And coming to the results, are significant findings on the extracted silica, what we have, when we could use a very simplified method to extract the pure amorphous silica from the system by soil gel process, especially we can, if we increase the concentration of the sodium hydroxide, then the yield of the silica which we are extracting from the agro residue increases. And post extraction of the silica, it's mandatory to wash this material with water washing in order to remove any impurities such as sodium chloride from the system. And also, when we use higher sodium hydroxide concentration during this extraction process, it actually decreases the surface area of the system by decreasing the pore volume. To have a more comprehensive understanding about how different kind of characteristics and properties affects the reactivity and hydration, we are actually in the process of conducting and evaluating different characteristics of the material, what we have what we have obtained by the acid washing. And also fresh and hardened property studies also being carried out to relate it with the reactivity of the system. And as we know, we say that this agro residues can be used as a supplementary cementitious material. However, we need to do some kind of pre-treatments and calcination to make them more appropriate or reactive when we are using as a substitute. So in order to know, is it economical and like, is it not like degrading the environment, we are doing a life cycle analysis on this material to evaluate the optimum pre-treatment process and calcination condition what we can give to the material. Yeah, we would also like to acknowledge the following departments such as Center for Health and Durable Transportation, USDOT, Idaho National Laboratory for providing the material, and Ashgrove for their support in analyzing the chemical properties of the material, and the Kentucky Transportation Cabinet for their support during this process. And also we would thank some departments in UOFL such as Con Center and Micro Nanotechnology Center for their continuous support in evaluating this material properties, and some other people who always like behind the back in carrying out this particular project. Thank you very much.
Yeah, thank you.
Well, thank you very much. So it's a very detailed study that you guys have done. So as we said before, so if you have any questions, please put them in the Q&A box and we'll get to those. But while people are putting their questions, I am not sure I understand the sol gel extraction that you were doing. Well, this is not a treatment to improve like you did before. This is just to evaluate the material, basically how effective it, how reactive it is going to be, right? The amorphous silica amount, you're trying to determine that, right? So what is the reason for, you were trying to wash it to get rid of the chlorides? So, but this is not something you would do before you use this material, right? The chlorides are just a byproduct there. What is the reason to wash the chlorides like this?
Initially, our major aim was like to convert this material as a supplementary cementitious material. But we could actually, if we could extract the amorphous silica from the system, then that silica can be used for different applications. Like we can synthesize this material, extract this material and synthesize it according to like nano size or macro size too for different applications. So it's not only for like cementitious application, but for say for example, we can use it as an absorbent or desiccant in any kind of process. So to do that, we need to have a high purity silica where we can't like leave any kind of impurities in the system. So that's why after the initial extraction, when we did the XRD analysis, try to understand whether we are getting a purest form of silica or not, we could see that the initial peaks when it showed that like a lot of sodium chloride is present in the system. In order to avoid it, we actually did the water washing. Then we carried out XRD to know whether the NaCl is gone or not. But still, we are not very clear it is completely amorphous. So we will be doing an XRF analysis to know what is the silica content in the system.
I see. So then there's a follow-up. So you see, you did the XRF analysis at the beginning, showed the chlorides as well. So that is actually, and you're using this as a SCM, that is ending up in your concrete, right? So it's going to be, so is that going to cause any durability issues, you think, later on?
Yeah.
Well,
that's one of the reasons why we need to eradicate this chloride from the system.
So at the beginning, in addition to the acid wash, if you do a water wash at the beginning, would that help with removing some of the chlorides? Maybe start with water wash and then go to an acid wash?
Yeah, water wash will help to some extent. So we did water wash at the beginning, and then we use acid wash. And then after that, we use water wash again. So there are multiple washing steps, I would say, to try to get rid of that impurity in it.
And one more question, maybe about the acid concentration you were talking about. So that is interesting. So the higher the concentration, of course, you were able to remove more of the alkalis, and in the leaching, you were seeing more of the alkalides. But then in the reactivity, you saw that 0.1 normal actually was giving you better reactivity, like removing more of the CH. So how do you explain that? So are the impurities actually then helping, or is it something else that's happening there?
Actually, we are still like confused about that part, because we don't really have the complete mineralogical composition of the material after doing the acid washing, and also we don't have the oxide composition of the material. So we need to see those things and try to understand what exactly is going in the reactivity phase.
But yeah, that's another thing. So did you do an XRF after the treatments?
Not yet. We haven't done that actually.
Okay. Okay, interesting. And then one last question. So what happens if you use the ash as is? Is there, did you try anything like that? Look at the reactivity without any treatment?
Yeah, we actually did that as well. In terms of like the thermogrammetric analysis, what we did to understand what is the calcium hydroxide consumption over there, we could see that it actually like has a higher amount of CH in the system. But thing is like there are some kind of reactive silica in the system. It reacts with CH to form the secondary CH. But since we have a higher amount of carbon in the system during this particular TGA protocol, it actually can calculate both the calcium hydroxide decomposition in terms of water, and also carbon dioxide, which is evolved from the system, also being calculated from this. So if we have if we use a material without any kind of washing, or like only water washing, then it will have carbon in the system, which also get accounted when we are like calculating the CH, calcium hydroxide. So which is actually erroneous in nature. Although it actually gives some amount of reactivity, we are in the process of like doing some other techniques to know exactly if we are using if you are not using any kind of reactive treatment to the ash, how that actually affects the reactivity. We are actually doing something on that also.
Yeah, because this is, adding extra cost, right? Extra cost, extra process. So I was wondering if, what if we just use it as is? How would it compare to the fly ash? And the fly ash that you were using for the 20% replacement, is that in C or F?
It's
when
a
you were
F fly ash.
F fly ash.
F, class F fly ash.
Okay, so those calorimetric graphs are that. Okay, very interesting. Well, great. I mean, the SCMs, I wanted to also say, they are not just helping the environment, they're also helping, with the durability of the material later on, with the lower permeability. You actually get better material, better concrete out of it. So, well, thank you very much.
Thank you.
Thank you.
And I don't see anything on the QA, so I will just move on to our second presenter. So Dr. Mohanad Abdulaziz. Hi, Dr. Abdulaziz. So he is an assistant professor who joined recently our Division of Natural and Built Environment within the School of Science and Engineering at University of Missouri, Kansas City, and where he brings his passion for teaching, research, and innovation in structural engineering. Dr. Abdulaziz earned his PhD from Missouri University of Science and Technology, where his work focused on developing resilient infrastructure systems using full-scale composite bridge components. And his research explores two main areas: the smart cities, which aim to make urban life more sustainable, efficient, and connected, and advanced computational modeling of the built environment. Here at University of Missouri, Kansas City, he leads hands-on research involving large-scale testing and the use of cutting-edge materials to strengthen and retrofit structures. There's also deep expertise in finite element analysis and using tools like ANSYS and LS-DYNA and Abacus and similar computer software. So, Dr. Abdulaziz, welcome. I will turn it over to you for your presentation.
Thank you, Dr. Holman, for this kind, introduction, and also thank you for the CHDT and MCTI for this opportunity. My presentation titled Embracing Innovative Strategies for Sustainable and Resilient Bridges. The presentation outline include the motivation and then the background, innovative strategies, conclusions, and finally with the acknowledgement. So I'm going to start by defining these two important terms, but in a different way. Sustainability ensures long-term function through infrastructure rehabilitation, and also the resilience is the enabled system to adapt and recover. Now, the question is, how do sustainability and resilience complement each other in ensuring the long-term functionality and adaptability of an infrastructure system? Can we? So there is a huge, challenge so far. So according to the U.S. Bridge Conditions 2024, and this is the source of the Federal Highway Administration, as we can see between the year 22 and 24, almost like 4% increase in the number of the bridges they are in the fair condition. And there is the good condition here, it's decreased. And as we can see here, if we're gonna add up the fair and the poor condition is almost 56% of the total number of bridges, which is almost 630,000 bridges in the whole nation. So this is really, something really alarming. And we're still with the challenge so far. So as we can see here, this is the number of bridges need work by the type of repair. We can see here rehabilitation for widening, rehabilitation, and also there is the dig rehabilitation replacement, bridge replacement. So if we're gonna add all these, percentage, together, we're gonna reach to the number of 43% rehabilitation, and there's the 35% replacement. So 1 out of the 3 US bridges still need to be replaced or repaired. So rehabilitation and retrofit techniques are really in a huge demand. So let's do some numbers here. So the total number of bridges in the United States is 621, or almost 622,000. These bridges, can be classified in these 3 categories. Steel bridges 33%, and there is a conventional reinforcement and concrete bridges 42, and there's the pre-stressed concrete 25, as we can see here. So mainly is the steel and the concrete here. So now, the main causes of bridge collapse, as we can see, it's a huge list. Started with the flooding and ended up with the earthquake. We are going to focus, today on these 2 things here, the earthquake and also the others, mainly, the corrosion for the steel bridges. So as we can see, this is the National Seismic Hazard Model 2024, and estimated that the around 49 million people are likely to experience a damaging earthquake in the next 50 years. So the question is how to mitigate earthquake damage for our infrastructures, modern infrastructure system, and also the bridge elements. The other one here is still in the background. So US drivers lost over 4 billion hours. And I couldn't imagine, honestly, the number for the first time. And this is for the Transportation Analysis Firm, the INRA, IXD.org. So, here, US drivers lost over 4 billion hours in traffic, costing the nation 74 billion in lost time to the congestion. This is in just 1 year, 2024. And you can do the math for the 4 billion, how many, years. And also the work zones, as you can see in this pie graph here, the pie diagram, sorry. So the work zone is 10%, causing this delay among, all the other factors. So as we can see here, there is the seismic, hazard, and also there is the congestion. So we need, to ask ourselves, so what's the solution here? So what's required to surmount these significant challenges? What we need, honestly, is the innovation. Innovation in what? In new construction methods and technologies, and also the advanced material for rehabilitation, and finally, for the evaluation techniques. So let's start with the new construction method and technologies. So ABC, the accelerated bridge construction, rely mainly on the prefabricated bridge elements and system. One of the indispensable elements in this assembly is the columns, and the ABC represent a paradigm shift in the bridge construction for today's infrastructure and modern, nationwide systems. So what's the advantage of the ABC, the accelerated bridge construction? First of all, the site constructability, increasing, the time here, so reducing the time of the total project delivery time, the work zone safety by reducing the exposure of the workers, in the hazard, zones, and the traffic impact, and also the on-site construction time, which is, related to this one for the total project time, and the weather-related time is going to decrease all these traffic and the on-site construction time, the weather-related time, and increase mainly the safety in the work zone. The ABC seismic applications, we want from the extra bridge construction, the continuity of the load path and the load reveals reversals, seismic events, development of cyclic and elastic deformations, maximum forces moment occur at the prefabricated moments connection. This is very important. So with the connections, either with the bend, which is the pocket connection, or with the footing with the socket connection, and the certain element material behaviors may cause rapid loss of the cyclic resistance, and this one due to the local buckling and also the strain concentration. So in general, we need to reduce the seismic mass and definitely efficient use of materials and improve strength to mass and stiffness to mass ratio. I think we are asking too much here. Can we achieve all these kind of aspects? So let's see. So we propose the hollow core column. It's an innovative column, consists of the hollow core fiber reinforced polymer concrete steel bridge column. And this one consists of the FRP tube from outside, and there's the steel tube, hollow steel tube from inside, and the concrete sandwich between them. The concrete is just like a gel. There is no reinforcement, just the concrete, acting like a spring between the steel tube from inside and the FRP tube from outside. What are the advantage of this kind of a novel column? So 60 to 75% less concrete material and lower freight, cost. And definitely the FRP tube as a stay in a plate formwork, as we can see here. With the on the outer the steel column and the concrete placed between them, and we use the self-consolidated concrete, the SCC one. And this is the steel tube active flexural and shear reinforcement, as you can see here. And finally, it's the high corrosion resistance due to the FRP tube from outside. The construction method of the hollow core fiber concrete steel column consists of cuts in place elements. And this one here, the cuts in place, as we can see from the previous picture, we have seen in the previous picture. And this is the hollow tube inside, or it's going to be the prefabricated element, precast element consists of the footing with the hole, and then just bring the column inside, as we can see here, and then do the injection for the high strength grout between the embedded steel tube inside the footing. And here is a picture from the the construction of the hollow, larger scale hollow core, I mean, fiber concrete steel column. And as we can see, this is the caging for the footing, and this is this placing the steel tube inside the footing, and then the FRP tube from outside, and we have a two type of the glass, I mean, fiber tubes, and then constructing the head or the mimicking, I mean, the bend of the column. Now, after this one, lifting the column as like two pieces, this is the column with the embedded steel tube here. This is this part, this portion, into the footing. And we some adjustment inside, I mean, the footing, and do the high strength, I mean, grout, and the column, as we can see here, is ready to be tested as a large scale column. So what we are looking for in high seismic areas, inelastic ductility is required. So according to the, I mean, this is the ductile design activity, which is applied on the displacement based method. This is different from the traditional ductile design, which is because sometimes the Ashton coefficient method. In general, I need the capacity, I mean, higher than the demand. This is the main concept. So we now let's I mean do the experimental test on the this I mean novel column, and as we can see here, we implemented the FEMA 461/2007, the quasi-static displacement controlled cyclic loading with the constant axial load of 110 kips, corresponding to 5% of the axial load capacity, and this is it can include 2 cycles for each displacement amplitude, as you can see here. The matrix consists of, this is a continuous research. I mean, till now we are like investigating the footing here. We started, I mean, with the other like colleagues with the reinforced concrete column. As you can see, the aspect ratio is 4 different FRP tubes, which is glass and iso polyester, and also the steel tube, the thickness of the steel tube, which is the D/T between 32.5 inches to up to 1.125 I mean inches. This is the thickness of the steel tube. It's a huge matrix, and it's a huge also quantity of the largest scale tested column under this quasi-static loading. These are some videos from the actual test, and as you can see here, this is the hollow core column under the lateral quasi-static and also the axial load, and this is the steel tube from inside. And we need, I mean, to achieve this in elastic deformation. And typically for reinforced concrete column, I mean, this is the conventional one. You will see this falling, which is the concrete falling, I mean, off in the outer, in the plastic hinge region, and also proceed with the reinforced steel reinforcement buckling. I mean, at this is between 5 to 7, I mean, percent with the drift, I mean, ratios. But with in this novel column, we reached up to 14% drift capacity, which is really remarkable. And the buckling of the steel tube, this is the localized buckling of the steel tube at the joint here, the interface between the column and also the footing connection. This is started at 9% drift, which is really remarkable. Overall, very promising results. In terms of the strength capacity, as you can see, this is for the conventional column, and we reached twice the required strength, up to 8. I mean, this is for the moment, 8 to up to 900. I mean, kips fit, and for the drift capacity, twice the required. I mean, the lateral drift capacity, and we put the target here of 6, even though there is no specific, I mean, guidelines. But this was the target based on the tested reinforced conventional reinforced concrete column. We reach up like to 14 here. And for the energy dissipation, which is very important key factor, dissipating higher hysteretic energy, reducing the seismic demand on structure. For this column, the novel one, we reached to triple the energy dissipated compared to the conventional column. In general, what we need a column, a novel one, easy, to construct in terms of the modern, infrastructure, systems, and also post the damage. It's also, not difficult, to repair, to retrofit after an extreme event. So we defined the damage here. So the first one, either the damage is going to be in the column, this is the plastic, hinge region, which is a critical zone, where in this column, the plastic bending is designed to occur and absorb the energy during the seismic event. Now, the other one, it's in the footing connection. And this one is either due to insufficient steel tube embedded length or the poor concrete confinement here. So these are, the typical damage that we are anticipated, while testing such novel, columns. Now, the question, can I overcome these two damages here? So the first one, if the damage in the column itself, we will see the rupture of the FRP in the compression, side, either under the cycle is going to be tension compression, and also the steel tube buckling. But for the early stages with the FRP, rupture, we developed a rapid recovery system here. So we were able to repair, retrofit this column within, just 6 hours. And from this side, and this is the damage, as we can see here, severe damage, especially in the FRP, and there's the huge, loss in the confined concrete, which is here in tracheal condition between the FRP and the steel tube. So what's the proposed, rapid recovery system here? So from this, shape with the huge damage to this, column ready to be tested again under the same loading conditions. So first of all, we started by the wet lab fabric FRP, and here we use the high strength glass fiber fabric, and this one with the saturated with the epoxy resin, and we took this one as a blanket, and we wrapped the column under this region after definitely cleaning and taking all the loose concrete. And as you can see, we left the FRP, we just tied from the top and left it kind of settled for an hour. And then we put this sonotube tube as kind of a heat chamber. And we applied the heat gun here, to speed up the process of the curing of the FRP with the epoxy resin. Then we did this hole for the injection, and we use this one to inject the high strength concrete inside to just compromise the loss in the concrete in this region. And this is the column, as you can see, it's ready to be tested. And this process, it was within just 6 hours. So this is the first one, and we were successfully able to retrofit the column. So the system was show us a huge performance in terms of the after the experimental test, and also under the quasi-static cyclic loading, and also the system shows us it's easy to repair this in a very effective way and with a short time. Definitely, we want to cut the time, we want to cut the cost of the repair, but always maintain the high quality, the strength of the whole system. The other one, which is the damage, we said, there is, two types of the damage, either in the column or in the footing connection. The resilient connection for exterior bridge construction. This is a very important topic. So as you can see from the hysteresis, curves for the tested columns, one of the columns with the D/T 32, and here the steel tube, it was with the 0.5 inches thickness. As you can see, there is a huge pinching effect here. And we achieved the high strength, but not the required fat loops, which is very important for the energy dissipation aspect. And with this column itself, the connection, as you can see here, failed progressively. Because of the severe damage. This initiated at the lateral drift 6.4 and propagated, as you can see, to this picture here. So how to design a column footing connections able to achieve the full flexural strength and also the inelastic deformation required for modern bridge, systems under extreme events. So we said, okay, so let's bring a corrugated steel pipe. So we brought a corrugated steel pipe embedded inside the footing, as you can see here. And then the footing with the hole, as you can see, and the corrugated steel pipe embedded here inside. And this is the hole to insert the column with the embedded steel tube, and then doing, the injection. And the construction, stages, steps, it's represented by placing the corrugated steel pipe into the footing. And then this is the temporary one for the hole, as you can see here. And then we do like, the caging. And after this one, placing, the concrete. And after the setting of the concrete, we will be able to remove the temporary corrugated steel pipe, which is this one. And this is the, hole here, ready to insert the column into the footing. Now the new footing with the embedded corrugated steel pipe. So we achieved with this one, the corrugated steel pipe, it's more confinement, and for the embedded steel tube, in order, to achieve the inelastic, full inelastic, deformations under the cyclic event. After this one, as you can see here, so this is the footing without the corrugated steel pipe, and this is the footing after inserted the corrugated steel pipe. And we reach, up to 14.5, lateral drift capacity. With this one, the 14.5, as you can see, this is the column without any significant damage, just hairy cracks, as you can see here, compared to the footing without the corrugated steel pipe. And also for the hysteretic moment lateral drift, the red one is the column without the corrugated steel pipe, and this is the column with the the black one with the corrugated steel pipe. And the column designed for the seismic design category, as you can see here, even with D, it's engineered to undergo large inelastic deformation without definitely losing the strength. And this is what we have achieved with this a new column with the new footing connection. Now, still in the rehabilitation mode here for and using the new technologies, and also now we are going to talk more about using advanced materials and to improve and increase the lifespan of our infrastructure. So the total number of bridges in our state, Missouri state, is 24,600. 700, plus, they are like, still bridges. And we have the 300 of these bridges have like, the pile section, loss, due to, environmental, harsh environmental effect. So the Missouri state, it's, with the 7th largest number of bridges, nationwide, 52% of these bridges are older than their intended useful life, of 50 years. 9% of bridges structurally deficient, and we are still with the great C. Now, for the steel bridges with the steel H piles as a column, as you can see here, according to the Euro code, the recommended value for loss of thickness, this is in millimeter due to corrosion of piles and sheet piles in the freshwater and seawater. So here, after 75 years, after 100 years, we should, maximum 0.3 loss, after 100 years. This is in the section. And we are like, here fighting against the corrosion, which is a naturally destructive electrochemical process. Now, what's the reality? The reality, as you can see, there is, nothing. The section is not even a 0.3 inches, or after 100 years, 0.5, millimeters. The section is almost like, gone here. So or exhibit a large, localized buckling due to the loss of the section here, itself. So we need to come up with a novel repair method using the advanced materials to increase the effective stiffness of the section and then maintain the load path accurately from the deck to the footing. Definitely with the the implementing of the advanced material. So the novel composite encasement here include the concrete encasement confined by the CFRP, the carbon fiber reinforced polymer, and also using the headed studs inside just a mechanical interlock. These are all combined in the kind of like the encasement for the damage or the severely corroded steel H pile. And the concrete encasing here either is going to be the normal weight, I mean, concrete, or the polymer concrete, or the zero cement concrete, the geopolymer concrete. All of these, I mean, type of concrete have been used in the proposing this novel composite encasement for the repair of the damages H pile. So this is the H pile here, and we simulated the corrosion, as you can see here, by the milling, the corrosion. And this is the proposed composite encasement, which include the CFRP jacket and also the concrete and fill surrounding the corroded region here. As you can see, this is the kind of like a band-aid for the corroded steel H pile, damaged steel H pile. And we tested, this is also a huge, matrix. We tested, several steel H piles with the different, corroded severity here. This is back, when I was in the SNT. And as you can see here, we did the either like, the simulating the corrosion by either a cut in the flanges or a cut in the web, or the decreasing the thickness in either the web or also the flanges of the steel H pile. This is the actual test for the both steel H pile. As you can see, this is the column without the proposed novel composite encasement for the retrofit. And this is the column here with this severity corrosion level. We were able to transfer the local, buckling, as you can see here, from the damage section, which is, now repaired one, to the healthy section, as you can see here. And we achieved, the goal of the encasement, use of the encasement as a repair method. And sorry, as you can see here, this is a more close-up, picture here. This is the steel H pile, and this is the corroded, region for the steel H pile, encased with this, jacketing with the CFRB carbon fiber reinforced polymer, and also the concrete and fill. And we were able to move the local buckling, as you can see here, the damage outside this repaired region, which is, showing us, the repair method was successfully implemented. The other use for the advanced material is using the UHPC plates, ultra high performance concrete plates. Sometimes we call them, the panels, as you can see here, with embedded CFRP grid inside as a reinforcement here. So taking the advantage of the CFRP, the carbon fiber reinforced polymer as a grid here, as a reinforcement, and also the advantage of the high strength of with using the ultra high performance concrete. These panels going to be used, as you can see, as encasement also. These are like between 16 pounds to 40 pounds. So it's easy to by the workers to handle, and also to mount on the corroded region. This is the corroded region, as you can see here. We took the worst scenario as if there is no section here, the loss of the whole section, 100% of the whole section is lost. And then we did some alignment to the section, and after the alignment we put the UHPC panels with the embedded CFRP grid. And this is the H pile, the H pile here. We tested the H pile under axial compression, just from the top and the bottom, as you can see, with the self-sustained system here, testing system. This is the steel H pile after the retrofit repair using the panel. And in general, as you can see here, using the UHPC plates, we were able to, this is the unrepaired one, this is the corroded one, And we were like, with the capacity with the repaired one up to 3 times the unrepaired steel H pile. So we're using the ultra high performance, concrete plates. Now with the composite material, the jacketing system using the CFRP and also the concrete infill, the target for the healthy, by the way, the squash, load for the healthy section without any corrosion is 600. With the repair, even like using the composite encasement for the corroded damaged column, using the CFRP and the concrete infill and also the headed stud as a mechanical interlock, we were able to reach up to 700, more than the load of the healthy section without any even corrosion. And this is the advantage of using the advanced material in the whole retrofit method. Now, for the real world, here localized measurements, and now we are moving to the evaluation techniques. So as you can see, this is the column, before the test, and this is the steel tube. And if we're gonna look, close, to the steel tube here inside, all these strain gauges have been mounted inside the steel tube. And me, I took almost like a week, crawling inside the steel tube to attach all these strain gauges. And also there is a high definition camera inside to capture the localized buckling at the interface joint. And also we use the strain gauges here, embedded strain gauges for the concrete shell between the FRP tube and the steel tube to measure the strains in the concrete under the tension and compression cycle. For the steel H piles, we use also strain gauges on the outer side of the CFRP jacketing here, the CFRP tube, and also the many strain gauges mounted on the steel tube inside this repair, encasement. And also there is a strain gauge also inside, very close, to some locations to the headed studs. The reason I'm explaining all this, a real world, localized measurement. Why? there is a reason about this one. So now we're still in the localized measurement. As you can see, it's time consuming and very, let's say, also expensive. And at the same time, there is also, we put a lot of these strain gauges, to overcome the loss of these strain gauges while performing, the test at some stages, like for at the early stages of the lateral drift and also the final stages of the lateral drift. Definitely, we're gonna use, some of the strain gauges. We're gonna also remove some of the LVDTs, due to the huge lateral drift. And for this reason, these are the results, obtained from these localized, measurement. As you can see, they are very, very important for us from the experimental test. For example, these are the readings for this strain gauges inside the steel tube, and it showed us, using the corrugated steel pipe inside our footing connection, we achieved, the embedded length of 25 was very, efficient and sufficient in this case, because after 20 inches inside the steel tube, and this is from the face of the footing. This is the face of the footing. After 20 inches, there is no more reading in strain gauges. So that's been, it's not even like MCTI, which is the part of the 5 inches. And also here, the strain gauge is mounted on the FRP tube. And as you can see here, we reach up like this is the sliding between the relative movement between the concrete shell and also the FRP tube, and also we put the relative movement between the FRP steel tube and also the concrete shell inside. Moving to the steel H pile, we have from the strain gauges, we got the bond stresses compared to different distances of from the loaded end, and this is give us the bond stresses, which is very important to also characterize and define the bond and how we are going to use it as a model, even if I want to implement this bond stresses into my advanced by using multi-physics, software models. And the readings here for the, as you can see, this is the FRP jacket hoop strains, readings. This is from the strain gauges mounted on the FRP tube during, the test for the novel composite encasement. So we use all these localized measurements. Very, very important to come up with the validated, solid, finite element model. This model, we are going to use it as a platform to expand our, research here scopes, definitely beyond, the experimental test. And as you can see, the goal is to achieve a comprehensive predictive simulation of the entire structure. Now we are moving to, not, to the localized, locations here, to the whole entire, structure using this multi-physics advanced, softwares. And this is the main goal for the long term and the future, because providing a monitoring system, this one is very important, is fast and easy to deploy with the continuous data reporting. This is from the experimental data capabilities. Definitely is going to us, giving us, some alarms, and also, no line of sight, required. And this one establishing a structural health monitoring system integrated with the finite element, analysis software. And this is the leads, to models with high complexity and maybe surrogate model-based method we are going also to use. Rely on the experimental measurements, the localized one. This is for the H pile, and this is the readings on the CFRP tube and the corrugated, the damaged, corroded steel section here, severely corroded one, and also the concrete, infill, or the hollow core fiber concrete steel column, the hollow core column, either on the FRP tube, as we can see here, this is the rupture of the FRP from outside, and this is the footing with the hole, and this is the corrugated steel tube, and this is the concrete between the corrugated steel tube and also the steel tube from inside. So the conclusions, my conclusions maybe is different because it has a goal. So the goal is to have a sustainable and resilient infrastructure systems, allowing to reduce life cycle cost and increase the system safety, and definitely maintain always the high quality strength and maintain the integrity of the whole structure. So with the conclusion, I would like to say we need to think differently. Shifting from the conventional practices to smarter, more sustainable bridge engineering. And this one relying on the more structural recovery oriented design and different construction techniques for, modern infrastructure systems, using the advanced material, and finally structural health monitoring with the oriented finite element method, implementing the finite element method. So we must, rethink on how to design and rehabilitate the bridges. Definitely traditional methods, fall shorter, and of modern, needs of resilience, sustainability, and implementing these novel new construction techniques, advanced materials, we can create adaptable, efficient, and longer, lasting structural bridge element. So I included here some references if you want to, learn more about these experimental tests, and these are from the recent published articles in this year, 2025, and also the technical report with the Department of Transportation. And finally, I would like to thank all the agencies supporting and also the companies supporting our research, and mainly the Department of Transportation and the Missouri Department of Transportation. Thank you. Any questions?
All right. Thank you very much, Dr. Mohammed. That was just so very nice presentation and very interesting new designs that I've never seen before. So And well, I had one question about the H piles. So the corroded H piles that you're putting the jacket around to strengthen the corroded section.
Yes.
Are you using any kind of corrosion measures in the new concrete? Because, you know, even though it is structurally strengthening that section, I would be worried about the steel that is inside the concrete and then the steel that's outside. So at that intersection, that there may be later onset corrosion because of the high pH versus, you know, low pH environment difference for the same steel.
Well, I mean, very interesting question, Dr. Holman. We are thinking about our repair, I mean, method here, technique, as a kind of like emergency repair, I mean, technique. So we have a section, I mean, which is a dispersible element, a column, and I mean, the whole bridge. And we need now, I mean, just like, I mean, to put it back, I mean, to be a functional, I mean, with the high strength and the supporting, I mean, the whole system. So definitely, I mean, for the long-term, let's say, I mean, durability and considering all these, I mean, the aspects that you mentioned, I mean, we didn't consider this one because, I mean, we are, I mean, really looking, I don't want to say the short term, but I mean, we are really looking, I mean, just, I mean, to repair, I mean, the column and definitely increase the effective stiffness of the, I mean, the loss, I mean, section. By the way, even in our repair, I mean, technique, we considered, I mean, the worst scenario. There is, I mean, a gap, just like, I mean, a void, air. There is not even, I mean, any use of, like, I mean, the remaining steel. But, I mean, back, I mean, to your question, no, I mean, we didn't, I mean, do any, like, I mean, or like measure, I mean, this one. It's a very good, like, also idea, I mean, to, I mean, put it for the future works. Thank you for this one.
So, I mean, it could be just even covering it with a thinner mortar section that's, you know, has the similar qualities that the jacket has. Just to prevent, just to keep the same pH environment and the overall column. Not the whole big jacket, but just cover it with a thin layer of mortar might be useful to prevent it in the long term. And then one more question I had was about the repair in the first one, in the hybrid column that you had the FRP tube on the outside and steel tube in the inside. So you put new FRP, you cure it, and then there's a hole that I see at the bottom. That's where you inject the new concrete, right? Is that a concrete or mortar section that you're pushing through that hole?
It's a mortar, high strength mortar.
It's high strength mortar you're putting.
Yep.
Okay. And the original column, was that mortar as well, or was that concrete?
No, it was the self-concentrated, I mean, the SCC concrete.
So,
We use
okay,
the
so it was SCC concrete, and then, but then when you're repairing, you're just pushing high strength grout or mortar.
Yeah, yeah, you're right.
Nice, okay. Okay, very interesting. Then the corrugated pipe that you put into your foundation, that is not galvanized, right?
Well, I mean, there are like, I mean, two types. One of them, the galvanized one, as you can see, and definitely, I mean, some of like, I mean, the other colleagues recommended, I mean, to use, I mean, not the galvanized one, but this one was like, I mean, the available at that time. I'm gonna say, I mean, most of these, I mean, by the way, I mean, projects, I mean, when I was a PhD and also a postdoc. So that one was the available in the local market with this diameter, which is the 36 inches. Because I mean, we were like very specific. We don't want to exceed the dimensions. So that one was like, I mean, the available one. And I still remember I took my car and went like, I mean, to Jeff City to bring this one. So I mean, yeah, this one is the galvanized one.
Okay, I see.
Yeah.
But I mean, in terms of structural behavior, it should not make a difference if it's galvanized or just.
No, I mean, because what we are really, I mean, considering of like using this, the corrugated steel pipe is to provide the more like hoop stiffness, I mean, with the confinement. So it's kind of like, I mean, capturing the steel tube and preventing, I mean, the extensive slip of the steel tube during, I mean, the seismic event, which is very, very important. Definitely with this bonding, I mean, the concrete between the steel tube, embedded steel tube inside the footing, and also this corrugated steel pipe is under tractility kind of like a condition. So it's applying, I mean, all the required pressure and the friction kind of like, I'm forced to maintain the steel tube in place during, these seismic events. So yeah, definitely it's not gonna, affect structure, the overall performance and the behavior of the element under this extreme event.
Okay. So thank you very much. Again.
Thank you. Thank you, Dr.
So
Holman.
yeah, I see some comments in that excellent presentation. So thank you very much for all the presenters in this today's webinar and all the attendees. So I hope we were able to transfer some important knowledge and some news about the ongoing research right now at both of our centers. So thank you very much, everybody, for attending, and we'll meet you in our next webinar, hopefully in about a month. Thanks.